Greetings and welcome, friends. We are talking today about proofs with perpendicular lines, section 3.4. You didn't even know you wished you knew what I'm about to teach you, but it is going to be amazing. Just you wait. So here we got finding the distance from a point to a line. This hopefully makes sense. The shortest distance between 2 points is a straight line or a line segment. The shortest distance from a point to a line is the segment that, or is the length of the segment that is perpendicular to that line. Okay, is kind of what this is saying. So the perpendicular segment is the shortest distance between the point and the line. For example, the distance between A and line K is AB. And that makes sense, for instance, if you've ever measured your height next to a door frame or something like that as you've grown up. You guys were probably adorable, I imagine. Just these, you're all growing up. Think of the nostalgia factor right now. Oh man, you guys. Oh, that would be slightly incredible. Yeah, I'll call it fully incredible if you were born at that height. So let's see. When you measure your height, you don't measure it diagonal to the floor. Maybe you've noticed that, right? Did you? No. No, you didn't, because you measured it perpendicular to the floor so that you'd have the appropriate distance, and that's how we calculate the distance from a point to a line, perpendicular to it. So if I want to, for instance, find the distance from a point to a line, which, by the way, these examples they give you right now these are like underhanded, like easy to catch. I think they set you up for success. They didn't make it too complicated yet. Tomorrow's lesson, it'll get a little more complicated. But here we go. I believe you have this sketch already. But it says, find the distance from point A. Man, I really like the inverted colors on these. To the line BD. So from the point to the line. Here we go. And then we've got some options. We know some coordinates. And I'm not going to measure from A to B to find that distance. I'm not going to measure from A to D to find that distance. I'm going to measure from A to C. And why is that? Because that is perpendicular to the line, right? So that's going to be the shortest distance. That's what we would be referring to if I want to find the distance from the point to the line, right? Does it make sense? And just to verify, notice I happen to know this is perpendicular even if this wasn't labeled, or I could verify it. The slope of BD happens to be up 1 over 1, up 1 over 1, and the slope of AC happens to be down 1 over 1, down 1 over 1. They're really just hitting these boxes at the 45-degree angle there, and so yeah, there's going to be 90-degree difference there. It's not too shabby. But however, now, if I want to find this distance, I'm going to need some sort of distance formula, which you guys fortunately have smuggled into my classroom in your brain boxes, which is what you're right. You remembered? Did you remember to pack it? You guys remembered to pack it. Yeah, it's this thing, the distance formula, which is also actually able to be determined using the Pythagorean theorem. The distance formula is just its cousin. And if you found, right, this and this, you could do a squared plus b squared equals c squared. You end up getting the same thing. The distance formula is just convenient that you don't have to reinvent the distance formula every time you do a distance problem. So let's label our points. Point A is -3, 3. Point C, sorry, is the one we're working with, was 1, -1. And if I label these, I'll label this my x1, y1, and this x2, y2, just to ensure that I plug things all in the right spot. Question, comment, yes? Does it have to be in that order? Absolutely it could. Yeah, and you might intentionally do that at times if for some reason you saw the math was going to be slightly easier in doing so. So yeah, you definitely could do that, and that would work out. I don't have any. Maybe the math closet? I don't know. I don't know. I'm sorry. No worries. So let's see. AC, to find the distance, right, I'd Could have labeled this point 1 and that point 2. It doesn't matter. The distance is the same whichever way you go. Left to right, right to left. So let's plug it in. So the distance, let me get my right color here, is going to equal the square root of x2. So that's 1 minus x1. Be careful with the double negative, all squared, plus y2 minus y1 all squared. So equals the square root of 1 minus negative 1 is 1 plus 1. All right, did I make a mistake? Where's my mistake? Oh, I have like multiple 1s showing up here. You're right. There should have been another 3. Okay. So let's see. Where was my mistake? In the first thing. x1 minus x2. All right. Or x2, sorry, minus x1. There it is. All right. So minus a negative 3. My apologies, friends. And I need the double parentheses there. Plus, good thing I labeled these. You guys saved me there. This whole video would have been terrible if I didn't notice the mistake until the end. Negative 1 minus 3 and equals the square root of 1 minus a negative 3 is plus 3, so that's 4, plus negative 1 minus 3 is negative 4, all squared. Also, don't you dare, you heard me, don't you dare try to do this. That is like the most super illegal thing ever, because square roots or exponents cannot be distributed over addition or subtraction. That does not work. So don't just try to like cancel that out and make up some fake math shortcut for yourself. So let's see, 4 squared is 16, plus negative 4 squared is also positive 16. So it looks like I got the square root of 32 as my answer. And then I could simplify that. Well, actually, they didn't even bother, but let's simplify it. I like to simplify the radicals. Let's see, largest perfect square that goes into that is 16, and it goes in twice. The square root of 16 is 4 and rad 2. 4 rad 2 is the exact value. The approximated value, if you plugged this or this into a calculadora, is 5.7 units. Okay? And distance is positive. All right, so distance formula, good times. Yeah, you're loving it. Let's see, let's talk about some theorems here. Ooh, that means you guys could actually fill in your new like theorem packet sort of thing, right? If you wanted to. You don't have to. Let's see. Here I've got the linear pair perpendicular theorem. Wow. The LPPT. Actually, I've never called it that. It says if two lines intersect to form a linear pair of congruent angles, then these lines are perpendicular. Did I forget that one? My bad. Oh no, I told you to skip the constructions, so don't you worry. We'll do the constructions after the video. So guys, if these angles are congruent and they're a linear pair, then their congruence requires that they would both be 90 degrees, because x plus x equals 180, 2x equals 180, x is equal to 90, and if those are 90 degrees, then by definition of perpendicular, those lines are right perpendicular, or def of right angle. So that proof, you might end up trying that tonight. Who knows? That'll be a great problem. Here's the perpendicular transversal theorem. Man, these names, you gotta love them. In a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. I mean, this is really like a special case of the corresponding angles theorem, right? I mean, it's almost like not necessary to say. I guess, well, the only thing it saves is not with my work not having to go from, okay, def of right angle, let's measure is 90. These angles are congruent, corresponding angles theorem. By, def of cong, then I could say this angle's measure is 90. And then by def of right angle, then it's a right angle. And if it's a right angle, then those are perfect. I guess it does save me some time. But I think that one's kind of obvious. You guys buy that? Do you believe it?
I buy it.
You believe it. You buy it. You can take that to the bank. That's right. And let's see. Here's one more theorem for you, friends. Bing. Let's see if I can line them up. Line them up. Just like, there we go. No, not even. It's fine. My failure will forever be recorded on the internet, like most everything else I do. Let's see. Lines perpendicular to a transversal theorem. Man, this is getting longer here. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. I would almost want to call this, it's almost like a converse. Is it the converse? So let's see. Two lines are perpendicular. It's pretty much just the converse of that. Yeah. So yeah, if these lines are both perpendicular to the same line, then they are parallel to each other. That makes sense. I think so. Okay, let's do an example. Uh-oh, friends. All right. We're doing a proof. Woo! Here we go. So here we go. Use the diagram to prove the perpendicular transversal theorem. All right, they set us up. I believe I also set you up with their setup. Let's see, I'm actually even gonna look at this. I've got my own table here for my setup. Bam. Okay, statements reason. Here we go. I'm gonna say H is parallel to K. Everybody's favorite reason? Given. Gimme. J is perpendicular to H. Even better, ditto, or just given. All right, given. Gimme. So let's see, we're trying to prove the perpendicular transversal theorem, which is going to prove that J is perpendicular to K. All right, that's our goal. Does anyone see something that I could say that would be helpful in moving towards that goal? I want to prove this. Anybody? I'm trying to prove these are perpendicular.
I'm going to go on 2.
Someone says 2.
2 and 6.
And therefore they are congruent by the
Corresponding angle theorem.
And that's right. That's the theorem, not the converse. Wow. All right, that's the theorem, not the converse, because I already knew the lines were parallel, right? That was given. And now I'm making a statement about the angles, so that's why I used the theorem. If I was going the other way around, if I was proving lines parallel, given the fact that the angles were congruent, then this would have been the converse. All right, very good. Woo. All right, wow. Okay, so those are, those are congruent. Now, if they are congruent, their measures, I'm going to say, are equal. Does anyone remember that one? Oh, yeah. I think def of Kong is my favorite, even more than given. Def of Kong, right? If the angles are congruent, then the measures are equal. And vice versa. If the measures are equal, then the angles are congruent. That def of Kong will take you both ways because definitions are biconditional. All right, check this out. I'm going to say, all right, measure of angle 2 equals 90 degrees. This is actually pulling from this statement here. Does anyone know why that's true? How could that tell me this? Let me show you the sketch. Does anyone see why that would be true?
Because of the box next to 2.
Because the box next to 2. I mean, you're on the right track. It's a definition of perpendicular lines. We're close. I don't know, you guys are probably running out of space. All right, let's see. I'm going to say now this, measure of angle 6 is equal to 90. Let's see. Why is that true? We got it. Transitive property. In this case, it's property of equality because I was dealing with equality and not congruence. But I'm just fine if you guys say transitive, right, Alyssa? Mr. Waddy. That's right. Let's see. And I think I've got enough information to conclude J is perpendicular to K. And I know that this is a 90-degree angle. And I'm saying that since it's a 90-degree angle, these lines are perpendicular by def of perpendicular lines. All right, so we have just proven this theorem, which means we don't have to prove it ever again. We can just like use the perpendicular transversal theorem. This particular theorem.
No, ever.
No, we build on these concepts.
No, you said yourself.
No. Yeah, so you'll be able to, refer to the video. And
Wait, so you're saying if we're on a test, and it's like, prove that J is perpendicular to K. Like,
this is your new reason, yeah. So instead of doing all of that work, now you just say perpendicular transversal theorem, friend. Unless I specifically asked you to prove the perpendicular transversal theorem, you're not allowed to prove something by citing itself.
Like, right on the link.
The hyperlink to the video?
Yeah.
Well, but that's essentially what this is. You're referring to something that I've previously proven true, and now that's sufficient information for us to just be like, okay, we know what you're talking about. Keep going. Keep building more math, and that's how it works out. All right, so writing proofs takes a little time to get used to, but it's okay. Let's see. I think we're on our last example. I'm excited about this, guys. Ooh. Wow. Actually, this next example is a little bit sketchy. It says, the photo below shows the layout of your neighborhood. What? Like Big Ideas is watching me from the sky? This is weird. Wow. Actually, it looks like one of those, what's it? That's not Google Earth. That's like one of those bird's eye view shots from, what's the name of that real estate website that starts with a Z? Zillow. I was going to say Zulily, but no, my wife just ordered something from Zulily, and there was a box that I saw when I left my house today. I don't know, it's clothes. By the way, this video and the letter Z is brought to you by both Zillow and Zulily, where you can buy clothes or a house. There you go. So let's see, this photo shows the layout of your neighborhood. Or no, I guess it just is a neighborhood. But let's see. Maybe this is where you live. I don't know. Determine which lines, if any, must be parallel in the diagram. Explain your reasoning.
Yes.
All right, let's see. So let's see. I've got the names of these up here, 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 and here, and here. Okay. I've got perpendicular, perpendicular.
Yes.
TS? T is parallel to S. Why is that true? We're not used to these names yet, but two lines that are perpendicular to each other. Which one was that one? I think it was this one, right? Man, we're not going to remember that one. Lines perpendicular to a transversal theorem. Yeah.
Sounds fun.
Bam. All right. Well, I was able to at least abbreviate a little bit. Perpendicular is what that means, yeah. So that's the perpendicular symbol. Parallel symbol, perpendicular symbol. Let's see, looks like P and Q. And I think it's the same reason, right? Because here's perpendicular, yeah. I could also theoretically have shown by the fact that these two angles are supplementary and then consecutive interior angles converse, but really, friends, let's use our new theorems. All right, well, I think we're good. Let's call it a video, a video. Yeah, 20 minutes and 55